Okay, before starting this dynamics of circular motion, you should know few topics of circular motion. Like in circular motion, we did few things. Like the first one was angular velocity. I'm just revising some topics of circular motion that we will use here. Like angular velocity. This angular velocity was rate of change of angular displacement. Its direction is along the axis of rotation. Direction is along axis of rotation. After angular velocity, the next quantity is linear velocity. So the relation between angular and linear velocities, if a body is moving on a circular track, due to its motion on circular track, this body has some angular velocity. Along with the angular velocity, there is a linear velocity which is tangential to the circular track. If I say that radius of the track is r, then this linear velocity v is angular velocity multiplied by the radius of track. So this is the relation between angular velocity and linear velocity. V is omega r. Okay, just note it down. I will use these. And there's one more thing. Due to change in velocity, change in direction of velocity. Due to change in direction of velocity, body have an acceleration known as centripetal acceleration. And centripetal acceleration is just v square by r. This is centripetal acceleration, which is v square by r. Okay, after this centripetal acceleration, the next topic is, now let's start with circular motion, dynamics of circular motion. The next is centripetal acceleration. Centripetal force. Now, the dynamics of circular motion starts with the concept of centripetal force. So if a body is moving on a circular track, the direction of its velocity is continuously changing. If a body is moving on a circular track, then over that circular track, direction of its velocity is continuously changing. Its direction is continuously changing. Now, Newton's first law says a body cannot change its direction by itself. It needs an external force to change its direction. So the external force which change direction of a body moving on a circular track is known as centripetal force. So centripetal force is force that can change direction of body, direction of velocity of body moving on a circular track. So if a body is moving on a circular track, then it needs a force which can change the direction of its velocity. That force is known as centripetal force. Or in one line, you can simply say it's a force which provides centripetal acceleration. It's a force which provides centripetal acceleration. So the force which can provide centripetal acceleration is known as centripetal force. So you can write that your centripetal force is the product of mass of body and centripetal acceleration. So it's the product of mass of body and centripetal acceleration is v square by r. So this is the centripetal force, which is mv square divided by r. If you want, you can even write this as in terms of angular velocity. In terms of angular velocity, centripetal acceleration is m omega square r. So centripetal force, you can write that the expression of centripetal force is m omega square r. So this is the magnitude of centripetal force, mv squared by r, or this is m omega square r. So if this is the body of mass m, it's moving on circular track. This is the center of the track. Then this body will experience a centripetal force, Fc. The direction of centripetal force is along the radius towards the center. And this is the magnitude. It's mv squared by r, or this is m omega square. This is it. So its direction is along the radius towards the center. So this is the centripetal force, which is acting along the radius towards the center of the path. And this is the magnitude. A very basic formula-based question, just to know how to calculate centripetal force. A body So see, centripetal force here is m v square by r. Mass of the body is 2 kg. Its velocity is 10, so it's 10 square divided by r, which is 2. So the centripetal force is 100 Newton. So that was about the magnitude of centripetal force and the direction of centripetal force. But to solve problems of dynamics, you need much more detail of centripetal force. The first thing, say this is a circular track. Circular track. This is the radius of track. It's a body of mass m. It's moving with a velocity v on a circular track of radius r. So this is a circular track. The radius of the track is r. Mass of the body is m. This body is moving with a velocity v on the circular track. This thing. So to move on circular track, see if the body is moving on the circular track, then the direction of velocity is continuously changing. While moving on circular track, the direction of velocity is continuously changing. And Newton's first law says that body cannot change its direction of velocity by itself. It needs an external force to change its velocity. So to change this velocity, you need an external force. So this centripetal force is the requirement. Centripetal force. So to change velocity, you need a force. That requirement is centripetal force. To change direction of velocity, centripetal force is required. So this centripetal force is requirement. Direction of velocity on circular path. This is the requirement. Some external force will fulfill this requirement. External force acting along the radius towards the center will fulfill this requirement. I will give plenty of example to support this concept, but these two things should be in your mind. Centripetal force is just a requirement. When I say that centripetal force is mv square by r, it doesn't mean that mv square by r force is acting on the body. It simply means that body required that much of force. It simply means that body required a force which is mv square by r. It's simply a requirement for centripetal force. And you need an external force to fulfill this requirement. For example, say if planets are revolving around the sun, planets are revolving around the sun in almost circular orbits. So planets need centripetal force. Who provide that centripetal force? The gravitational force between the sun and the planet will provide centripetal force. So planet revolving around sun require centripetal force. Requires centripetal force. This is the requirement for circular motion. Now, who will fulfill this requirement? The gravitational force between sun and the planet gravitational force between sun and planet will provide this centripetal force. This is the first thing. So the gravitational force between sun and planet will provide the centripetal force. One more example. Okay, just can you tell me, in an atom, electrons are revolving around the nucleus. In atom, electron revolving around nucleus requires centripetal force. Can you tell me who will provide the centripetal force?
So electrostatic force of attraction.
Yeah. The electrostatic force between electrons and nucleus will provide the centripetal force. Electrostatic force between electron and nucleus will provide the centripetal force. So there is always a requirement which is in terms of centripetal force. Then there is a supply. Supply here is gravitational force. This is providing centripetal force. Supply here is electrostatic force, which is providing centripetal force. In few cases, friction can provide centripetal force. So is it clear that centripetal force is just a requirement? If you don't have gravitational force, say planets are revolving around the sun, and somehow that sun evaporates. Some evaporates and gets ended. then planets cannot revolve around the sun. Then planets will go tangentially. Then planets cannot revolve, then they will go tangentially. They can only revolve if this requirement of centripetal force is provided by some external force. Here, this is gravitational force. If you remove this external agency which is providing centripetal force, then body cannot move on circular track. It will move tangentially. It will go straight. Is it clear? Because
Yes, sir.
whatever we will do today in centripetal force will depend on these statements only. So that is the concept of centripetal force. After this concept, the next thing is mm, let's solve this problem. So we will solve two problems just to clear this concept. Then we will come to application part in your syllabus. Maybe these numericals would not help you directly in your school exams, but they will help in clearing this concept of centripetal force. So let's say this is a bridge. It's a bridge in this way. It's concave bridge. This is the center of the bridge. This is the radius of the bridge. This is a car. It's moving with a velocity v over this circular track. The mass of the car is m, so its weight is mg. Okay, so if I solve this problem, then this is weight. The normally action is acting in this direction, is perpendicular to the plane. This is the direction of normally action. So now we have to decide which force will provide centripetal force. There are two forces. One is N, another is mg. So when you have more than two forces, then the net force acting along the radius towards the center will provide centripetal force. So the net force which is acting along the radius towards the center is the one which will provide centripetal force. So what is the net force which is acting along the radius towards the center here? Say, we always take direction towards the center as positive. So we'll take N as positive and mg as negative. So this N minus mg will provide centripetal force. So you can say that this N minus mg is equal to centripetal force. So you can say that N minus mg is mv square by r. And your N is, it's mg plus mv square by r. So that is the value of normally action here. Solve a similar problem. I'm just changing the shape of the bridge. This is the shape of the bridge. This is center. And this is car. Also calculate normally action here. Calculate normally action here. See, this is the direction towards the center. So see, weight of the body is acting downwards, mg. The normally action is acting upwards. I need net force towards the center. So the net force towards the center is mg minus n. This mg minus n will provide centripetal force. So you can write mg minus n is mv square over r. Or you can say that your n is, it's mg minus mv square by r. It's okay. Let's do one more question. Say this is a rigid support. I take this string. I connected this string to a body of mass m. Then I apply force and this mass starts rotating in a circle of radius r. This is the length of the string. This is the length of the string. This is how it happens. Like this is your string. Earlier it was vertical. Yeah. So earlier your string was vertical. Then I take this string at some angle theta with the vertical. Then I tilted this string at some angle theta with the vertical. Then this string, it starts revolving in a circle of radius r. Earlier it was vertical. Then it tilted from its vertical position and then it start revolving in a circular radius r. Like if you take a thread, you connected a stone with the thread and you start keep on revolving that stone in a circular path. This is what we are doing here. So I'm just representing this initial position with the dotted lines. Then this thing, this string is revolving. This move at an angle theta with the vertical. And this is revolving in a circle of radius r. This is the radius of the circle. The length of the string is L, and this is the radius of the circle. It's revolving in a circle of radius. And this is the center of the circle about which it is revolving. From here to this initial position here, length is L. Here to here, this is stone now, this length is L. The R is the radius of the circle. So a stone see, this was the initial position, the dotted one. But now when the body is revolving, then body is here. Is the geometry of the system clear?
Yes, it's clear.
So this is the circular path of radius r. Okay, now tell me, this is your stone of mass m. Sania, can you mention all forces which are acting on this mass m?
Gravitational force.
Which is weight, right? Only acting in downwards direction. Another force which is acting over this mass m.
No.
Centripetal is the requirement. Okay?
Yeah.
We never draw centripetal force in your FBD free body diagram. Another force. Only one force is acting on the body.
Sir, I don't know.
If only one force is acting on the body, which is weight, then body should fall downward. There should be something which is balancing this weight, right? So that should be
Yes.
of forces more. One which is balancing the weight, one which is providing the centripetal force. Fazil, can you mention more forces there?
And normal react.
Which one?
Normal react.
No, normally action acts when the solid surfaces are in contact. There's nothing is contact. There's a string and that is revolving in a circle of radius r.
The tension of the string.
Yes. Tension. Tension will act. So if this angle is theta, then this would be theta again. Why is it theta? Which angle is this? Alternate angles, right? If I take this as theta, then this is theta. This is tension. Note what's the component of tension in this direction, upwards?
I didn't understand.
Sorry,
I didn't understand
what's the
the question.
component of tension T in this direction?
T cos theta.
T cos theta. And in this direction, this will be T sin theta. Note this tension is not given. So this T should not be in your answer. Like while calculating any numerical, first of all decide what are the given terms. This M is given, this theta is given, then this length is given, then this radius is given. T is not given. So you have to substitute T somehow. Anyways, if I take this mass M, what is T cos theta doing? This T cos theta is trying to balance this weight of the body. Say, if I connected a mass through a string and I'm revolving that mass in a circle of radius r, then continuously two forces are acting on the body. One force is trying to balance the weight, otherwise the body will fall downwards. There is another with force which is providing the centripetal force. So there is one force T cos theta which is trying to balance the weight, which is equal to mg. That's first equation. Then there is another force T sine theta. See, T sine theta is acting towards the center. So this T sine theta is providing centripetal force. Is it clear, everyone?
Yes,
Yes,
sir.
sir.
The next thing is you can divide 2 and 1. When you divide 2 by 1, this is T sine theta divided by T cos theta is mv square by r by mg. This m will cancel this m, this t will cancel this t. You will get tan theta is v square by r. So you can write your v square as rg tan theta. You can write your v as root over rg tan theta. This is how we can get velocity. Velocity is root over rg tan theta. Is it clear?
Yes.
This is how we use centripetal force. Every force which is acting along the radius towards the center will provide centripetal force. There's one more
Sir,
thing.
can you explain again?
Okay, the whole thing.
Yes, sir. Yes, sir.
This resolution was clear.
Yes, it's clear.
Yes, sir.
If this body of mass m is moving in this circle of radius r, like say it's moving in air, then there are two things happening. The one is Earth is trying to pull this body downwards. If this body is not falling downwards, that means there is one force which is trying to balance the weight of the body, and that force is T cos theta. So a component of tension is trying to balance the weight. So I write this as T cos theta as mg. Is it clear?
Yes, sir. It's clear.
There is another component of tension which is acting towards the center. So the force which is acting towards the center will provide centripetal force. That's why I wrote T sine theta as mv square by r. Right?
Yes.
Now you need this m. I don't know what's the value of t here. So I just divide 2 and 1. On dividing 2 and 1, this t gets cancelled out, m gets cancelled out, and I got velocity which is root over rg tan theta. Fine.
Yes, I understand.
The next thing is you can even substitute your r in terms of L. Say, I don't know what's the value of r. I can as well write this R in terms of L. So for this, you can take this right angle triangle. You can take this right angle triangle. This is O. This is C. And let's say this is M. In triangle OCM, you can use, this is perpendicular and this is hypotenuse. You can say that your sine theta is radius divided by the length of the straight. And you can write that the radius R is L sine theta. So I take this as equation 1. I take this as equation 2. I substitute 2 in 1. And V is root over its R, which is L sine theta, into G, which is tan theta. In the next section, you're supposed to calculate safe limit for car on a circular turn. So this is a real life application. Say you have a circular turn. If you have noticed, on circular turn, usually the speed limit is mentioned. Let's say I take a circular turn. This is the car over the circular turn. This car is rolling on the circular turn. And I say on this circular turn, the speed limit is 50. Let's say the speed limit is 100 km per hour. This is the speed limit. So speed limit means the maximum speed with which this car can move on the circular turn is 100 km per hour. If car exceeds this limit, let's say if car starts moving with a speed of 110 km per hour, then it will skid. Skid means it will move in this outwards direction and eventually it can topple. If this is the car, it's moving in this on the circular track. If this car exceeds that speed limit, then this will move outwards, and the chances that this car will skid in the outwards direction, and there are chances that this car can flip, this can topple, leads to an accident. Now, can you explain why this car cannot take a circular turn if its speed exceeds the speed limit in terms of centripetal force?
So the
Sir, it
centripetal
will.
force is provided by friction, and above that speed friction, there will not be enough friction to hold the car.
Right. See, say the mass of the car is m, the radius of the track is r. So the maximum force, like see, if the car is moving on a circular track, it will need a centripetal force. This car will definitely need a centripetal force. Someone here should be providing that centripetal force, and that force is basically friction. Friction is providing the centripetal force. How friction provides centripetal force, that we will see in the next section. But see, friction is providing centripetal force. So what do you think? Your centripetal force, I'm giving you two options for the safe limit, for the safe turn. Friction is less than the external force, which is providing the centripetal force, or your centripetal force can be greater than the external force, which is providing the centripetal force. So which condition should this system follow for a safe turn? Your centripetal force should be less than external force, or it can exceed centripetal external force. for safe turn? Answers. This is option A and this is option B. So which condition should hold if the car were required to take a safe turn? First or second condition? I need answer of each one of you. A.
Sir,
Yes.
sir, can you repeat the question again?
Yes. See, this car is moving on a circular track with certain velocity. The safe limit of the track is 100 km per hour. It's written that the safe limit is 100 km per hour. If car exceeds that safe limit, then it skids. Skid means if car is moving on the circular track, it will go out of the track. It will skid, and finally, it can topple in this way, and that can lead to an accident. So I'm just asking that for a safe turn, there are two forces involved. One is centripetal force, which is the requirement, and second is the external force, which is the supply. There should be some force which is applying the centripetal force. In the last few examples, there was one gravitational force, which was an external force, which was providing centripetal force. Then there was electrostatic force, which was providing centripetal force. In the recent example, a component of tension was providing centripetal force. So I'm just asking for a safe turn so that car does not skid. Which condition should hold? Centripetal force should be less than external force, or centripetal force should be greater than external force? Yes, Sanya.
Less than.
Less than, yeah. Because this is the requirement. Your requirement should always be less than supply. If centripetal force requirement exceeds supply, then eventually accident will happen. Noor,
Yes, sir.
the second cannot be true because this is providing centripetal force. Centripetal force could not exceed this thing. In this example, centripetal force is exceeding its external force. That's why body will skip. For
Okay,
safe,
sir.
your centripetal force should be either less than or at most equal to the external force. Then only your body will take a safe turn. So you have plenty of cases to calculate safe limit. The first and the easiest one is bending of road. The very first case is bending of road. So bending of road means this is a circular turn. On this circular turn, a car is moving. So car is rolling over this, not rolling over this circular turn with a velocity v. A frictional force is acting on the car which is towards the center. So to move in this circular turn, let's say the radius of the circular track is r. I'm taking the radius just from the center of the track. The mass of the car is in. So car of mass m is moving on circular track of radius r with speed v. So to move on this road on with the speed v, the car need a centripetal force. So the centripetal force required. Centripetal force required by the car is mv square by r. This first equation. So this is the centripetal force which is required by the car. Now, can you tell me who can provide the centripetal force? So, friction between tire and road will provide centripetal force. So, you can write that frictional force as mu n. In this case, the weight is acting. See, it's a three-dimensional diagram basically. This is the road, which is an xy plane. This velocity is an xy plane. And this is normally action, which is perpendicular to the road. So normally action is in z-axis along, and weight is also acting along z-axis. So this is weight, which is acting along z-axis, and there is normally action, which is also acting along z-axis. Say this is the track and this is the car. This plane should be clear. This is the track and this is the car. Car is moving in xy plane, but normally action is this perpendicular to the plane of the car along z-axis. Your weight is perpendicular to the plane of the car along z-axis. So your weight is acting perpendicular to the plane of the car. So that's why N, I can write this N is equal to mg. That's your friction, mu mg. Body, it's mu L mg. It's not sliding. So friction provides centripetal force. That means your centripetal force should be less than or equal to force of limiting friction. Your centripetal force is mv square by r, which is less than or equal to its mu L mg. This m will cancel this m. Your v square is less than or equal to its mu L rg. Its v is less than or equal to its root over mu L rg. So this is the velocity of which the body is moving. It's less than or equal to root over mu L rg. Is it clear?
Yes, sir.
Yes, sir.
For a safe turn, the velocity should be less than or equal to this thing. So what should be the maximum value of velocity if you use equality sign? It's like if I'm saying that x is less than or equal to 3. So what could be the maximum value of x? It's equal to 3. It's either less than or equal to 3. The maximum value is 3. So say in the same way, v is less than or equal to mu L rg. So what's the maximum value of velocity? It's root over mu L. So this is the maximum velocity of body. And we call this maximum velocity as safe limit. This is the safe limit, maximum velocity which with this car can move on a circular route. And solve this question. So car of mass 10 kg see the safe limit V max is root over its mu rg. So here mu is 0.2. The radius of the track is 10. Your g is 10. It comes out to be root over 20 meter per second. That you can write as 5 root 2, like 2 root 5. Sania, is it clear? So this is the maximum velocity with which this car takes a circular turn. If the speed of car exceeds this value, then car will skid, that leading to an accident. So, okay, tell me one thing. So, on which factor you think this safe limit depends here? Safe limit here. Yes, Fazil, on what factor the safe limit depends here?
Coefficient friction.
On coefficient of friction. Here, the safe limit depends upon the coefficient of friction, which is not very reliable because this coefficient of friction keeps on changing. It keeps on changing continuously. See, the coefficient of friction between the road and the tire can decrease on a rainy day due to water. The road gets slippery, and due to that water, the coefficient of friction decreases. Even with the regular use, the tire gets smooth. The friction between the tire and the road decreases. Depends here on coefficient of friction, which is not reliable. As friction between tire and road can decrease on a rainy day or with use of tire. The next thing is after bending of road, there is one other topic which is banking of road. Banking of road simply means raising the outer edge of the road. Banking means raising the outer edge of the road above the inner one. Okay, have you ever noticed that racing track in that Formula F1? Is that track flat circular or that track is tilted somewhere? Fazil, no. Have you observed that F1 tracks?
Yes, sir.
Are they flat circular tracks or they are tilted?
Slightly tilted.
Slightly tilted, right? Say
Yes.
if this is the F1 track, this is the F1 track. Where is it tilted? Tilted means this is the inner edge and this is the outer edge. One of the edge is bit tilted. Which one is raised? Inner edge is raised or outer edge is raised?
Outer.
Outer edge.
Outer. This is bit inwards and this is outwards. That raising the outer edge of the road is known as banking basically. We'll see why we bank a road. So banking simply means the outer edge of the road is raised above the inner edge. So a circular turn is not in this way. A circular turn is in this way. The outer edge a bit is raised as compared to the inner edge. That's known as the banking of the road. So this is the circular turn. Now this diagram should be a three-dimensional diagram basically. This is the inner turn. This is the inner turn. The outer should be raised with respect to inner term. So if this is the inner, outer should be here, slightly raised with respect to the inner term. But I cannot draw that three-dimensional figure here. So I'm just showing it like this way. That your outer edge, this is the outer edge, this is the inner edge. Outer edge is raised with respect to the inner one at an angle theta. So Sania, is the screen visible now? So that's your bank road, and this is your car placed here. Mass of the car is here. Have you seen that F1 race on television, on YouTube, anywhere? That F1 bike race and car race.
Yes, sir.
Okay, the track, have you observed that track, that circular track? Is that circular track
Yeah,
even? It is in level, or the outer edge is raised with respect to the inner edge? If you can remember. On F1 track, those racing tracks are even, the inner and the outer edge are at the same level, or the outer edge is somewhat raised with respect to the inner.
I don't know, sir. I
Mhm.
never noticed.
So then the next time you watch that race, just observe that the outer track is a bit raised with respect to the inner track. The thing is like this. Just give me 1 second.
Okay.
Yeah. So if this is your circular track, yeah, this is the circular track. So this in this way. This is the track, right? This track, if it is even, that means inner and outer edge of the road are at the same level. But it's not always at the same level. The outer one is raised a bit with respect to the inner. And the car is rolling like this. The car is rolling like this, obviously. The outer edge is a bit raised as compared to the inner. This is what we call banking. And, okay. So this is known as banking. So why we bank road? See, when the road was not banked, it was a flat road and a circular turn. Then only friction was providing centripetal force. But once you bank this road, not just friction, but a component of normal reaction will also provide centripetal force. This is the advantage of banking. By banking, along with friction, a component of normal reaction will also provide centripetal force. So it's not just friction which is providing centripetal force, but a component of normal reaction will also provide centripetal force. Now let's see how a component of normal reaction can also provide centripetal force. Mass of the body is m, so its weight is ng. So this is the normal reaction in here. If this is theta, then it can be easily proved. So if this is theta, then this angle, this one, this with the inclined plane. This angle is also theta, alternate angles. If this is theta, then this angle is 90 minus theta, and this angle is theta. See, this is straight line, and if I take angle here or here, is the same thing. This is normally action. This is the horizontal direction, and this is the vertical one. If this is theta, then this is theta alternate angle. This and this are perpendicular, so I call this as 90 minus theta. Again perpendicular, so I call this as theta. So you can take components of a normally action. One is acting in this direction, which is n cos theta. Another is acting towards the center, which is n sin theta. And moreover, the car have tendency to slide down the plane, so friction is acting up the plane. Sorry, so not down the plane. This car, due to inertia of direction, this car will try to move out of the center of the circular plane. This have tendency to move up the plane. So friction will definitely act down the plane. This is the center of the track here. You can take components of friction. This is one component, which is f cos theta. This is another component, which is f sin theta. Okay, now can you tell me what are the forces which are providing centripetal force?
N sin theta
Just n sin theta or plus f
and
cos?
F cos theta.
F
Have you
cos.
done this thing in your school?
Yes, sir, we done.
Yes.
You have done this thing. So n sin theta plus f cos theta will provide centripetal force. You can say that this is equal to centripetal force, which is mv square by r. That's my first equation. This n cos theta will balance these two terms. F sin theta plus mg will get balanced by n cos theta. That is equation number 2. This is it. So you can write this as like your mg is n cos theta minus f sin theta. That's second equation. Is it clear? The two forces which are acting towards the center will provide centripetal force. This force acting upwards will balance the two forces which are acting downwards. That's so that your system is equilibrium along y-axis. In the next step, you can write the value of friction. Friction is always mu. If I substitute the values of friction, is 3 in 1 and 2, then I will get this mv square by r is n sine theta plus f, which is mu n cos theta. So you can get that your mv square by r, you can take this n as common, it's sine theta plus mu cos. That is equation number 4. Next, when you substitute this value in 2, you will get mg is n cos theta minus friction, which is mu n sine. So your mg comes out to be n. It's cos theta minus mu sine theta. That is equation number 5. So you can divide 4 and 5. So when we divide 4 and 5, we will get mv square by r into mg is n sine theta plus mu cos theta divided by n cos theta minus mu sine theta. That is equation number 6. So this n will cancel this n, m will cancel this n. So we'll get that your v square over r g is sine theta plus mu cos theta over cos theta minus mu sine. So you can write your v square as rg. It's sine theta plus mu cos theta by cos theta minus mu sine. You can leave your calculation here, but just to keep this thing in standard form, you can keep on dividing. You can divide numerator and denominator by cos theta, just for a simplified expression. Sine theta over cos theta. I'm just dividing numerator and denominator by cos theta. Mu cos theta by cos theta over cos theta by cos theta mu sine theta by cos theta. So the cos theta by cos theta is 1, cos theta by cos theta is 1. So v square is rg. It's tan theta minus mu by 1 minus mu tan theta. So yours v square is, it's rg mu plus tan theta by 1 minus mu tan theta. Or you can write your v as, it's root over rg. It's mu plus tan theta by 1 minus mu tan theta to the power half. So this is the safe limit. There is one more, is it clear?
Yes, sir.
Yes.
So along with friction, you have one more factor which is providing the safe limit. So obviously safe limit would have increased. So just to see that if I remove friction, then what will happen? So we introduce a term which we call optimum speed. Optimum speed means safe limit on putting mu equal to 0. So if I put mu equal to 0, then your V comes out to be, it's Rg, it's tan theta plus 0 over 1 minus 0 to the power half. So V comes out to be root over Rg tan theta. V is root over Rg tan theta. So this is the optimum speed, means this is the safe limit with ignoring friction. Means your road and tire doesn't have friction in between, the smooth road, smooth tire. Then again, due to safe limit, due to this banking alone, your system can have some safe limit. So optimum speed means due to banking only. And this banking is not only in road, even in railway tracks. Whenever there is a sharp turn on the railway track, then the outer rail is bit raised with respect to the inner rail, so that the banking can give the safe limit. Okay, after banking of road, there is one more thing which is known as bending of cyclist. Have you seen bike racing?
Yes,
On the circular track, the rider is straight or is he bend his bike towards the center of the track?
bends his back.
It's bent.
If you observe it carefully, the greater his speed is, as he keep on increasing his speed, he keep on uh, bending himself towards the center of the track. As his speed is his increases speed on the circular track, the angle of bending, like he keeps on bending himself towards the center of the track. So this is the circular track. This is the center of the track. If this is a cyclist or a biker, someone who are moving on two wheeler, he keep on bending himself with the center. So theta is the angle of bending with respect to vertical. So this is theta, which is the angle of bending with respect to vertical. So why a two-wheeler bend his bike or his cycle on a circular turn? The reason is due to bending. See, if this is the cyclist, this is the cyclist. This is the weight of cyclist, and this is the normally action. If the cyclist is straight, then normally action will act in upwards direction. But since he bent his cycle, the normally action is acting at an angle. You can take components of normally action. This is n cos theta and this is n sin theta. So it's very clear that n cos theta will balance the weight, and this n sin theta will provide centripetal force, mv squared by r. That's it. So if I divide 2 and 1, then one will get that n sin theta by n cos theta is mv squared by r into mg. M gets cancelled with this n gets cancelled with this n. Tan theta is v squared by rg. So your v is its root over rg tan theta. So if you see this carefully, the velocity or the safe limit that you were getting due to banking of road, due to raising the outer edge of the road, you are getting the same effect just by bending the cyclist. So that's why cyclists bend his cycle on a circular turn, so that a component of normal action can provide the centripetal force. You will get the same effect by bending a cyclist that you were getting by banking of road, by raising the outer edge of the road. So there's one small topic which is known as centrifugal force. Centrifugal force. Okay, do you remember what are non-inertial frames? Although usually from this part you don't get much numericals, you get basically conceptual questions. But we will do numerical first once I finish the centrifugal force. So, what were non-inertial frames? We have discussed non-inertial frames earlier. No one remember. Non-inertial frames was frames which were accelerating with respect to Earth or frames which are rotating with respect to Earth. So centrifugal force is basically a pseudo force which is acting in rotating frames. And rotating frames are basically non-inertial frames. So the pseudo force which is acting in rotating frames, basically non-inertial frames, is known as pseudo force. Its magnitude is mv squared by r, or you can write this as m omega square r. This one is its magnitude. Its direction is along the radius away from the center. So if this is a rotating frame, this is the axis, it's rotating with an angular velocity omega. So body placed on the frame will experience a centrifugal force which is away from the center. It's a very common observation if you have ever tried a ride which is rotating. If you sit in a rotating ride, you will experience a force which is pulling you out of the center of the ride. So if you have a ride which is rotating about certain center, then you will experience a force which is trying to pull you away from the center of the ride. That force is basically centrifugal force. It's a pseudo force. We have already discussed what is a pseudo force, but this pseudo force acts in a frame which is rotating. Its magnitude is exactly equal to that of centripetal force, but its direction is opposite to the direction of centripetal force. That's centrifuge. Okay, now let's discuss the question that I have left, like on the using bending of rod, why I have taken sliding friction and why we have considered limiting friction, not the kinetic one. For that thing, consider this circular turn. It's a circular turn. Let's say this is the car, the tire is rolling over the circular turn. So the tire is rolling in the forward direction. In the forward direction, this car will experience a rolling friction, but rolling friction is negligible. So I'm not considering it. But now, since the tire of the car is on a circular turn, so a centrifugal force will act on the tire that will try to move this tire sideways. It will try to skid the car. Do you know what is skidding? Skidding means?
To slip.
Yeah, slipping. The tire can roll either in the forward or the backward direction, but sidewise it can skid. So what happens when you move a tire on a circular turn, then it rolls in the forward direction and the backward direction. But due to centrifugal force, this tire tried to slip horizontally. And then, so if it's trying to slip, then this is sliding. It's not rolling. It can roll in the forward and the backward direction. It can't roll sideways. So this is sliding. So this tire will try to slide sideways, which is prevented by frictional force. So that's why the friction is not rolling. I'm not taking friction in the forward and the backward direction. I'm taking friction in the sideways direction. So that's the first reason why the friction is sliding, not the rolling friction. The second one, why I'm considering limiting friction, because the friction does not allow this tire to get slip. This tire is trying to slip, but friction is not allowing it. Friction is basically holding this tire from slipping. So that is the reason why I consider that thing, the sliding friction and the limiting one.